the nice introduction, and also, well, thanks to all the organizers for putting together this really nice school and for giving me an opportunity to talk here. So my the set of lectures will be basically about quantum optics and resonant atom light interactions. Judging from some of the conversations I had, it seems like there's people in the audience from a wide variety of backgrounds. So what I thought I'd do first, so most of my lectures will actually be on the Blackboard, but what I thought I'd do first is just to kind of give you an introduction, a big picture level of quantum optics and atom light interactions, to give you a flavor of the kinds of problems that we're interested in, and also to eventually talk about so quantum optics. In quantum optics, words like emergent phenomena, many-body, etc. Those are not words that I ever learned about in quantum optics that you won't really see in a quantum optics textbook. It's honestly not things I necessarily know a lot about, but also what I hope to do in the lectures is to kind of convince you that these kinds of words are really kind of, I think, the future of quantum optics, and they're really the kind of interesting, underlying them are a lot of interesting questions and possibilities, which really drive my research today and in the foreseeable future. Okay. So again, what I'm presenting here is just meant to be a kind of big picture. If you're, of course, free to ask any questions you want anytime. But then later on, I hope to kind of get into the theory a little bit more deeply. So when we talk about atoms interacting with light, the first thing I should do is kind of define an atom for practical quantum optics purposes. So an atom can be almost any generic atom. In practice, people don't really work with hydrogen, but if you want to think about hydrogen, that's sufficient. So what is hydrogen? What is a hydrogen atom? Well, we know that we can quantize it in quantum mechanics. And then when you look at the electronic states, you get a set of discretized levels. So in hydrogen, the ground state is the 1s orbital. If you go higher up in energy, the first excited state is a 2p orbital, and so on. And then in quantum optics language, we like to denote energy on a kind of vertical diagram. We'll call this state here a generic ground state G, and this first excited state some abstract state E. And the way that in practice you go from the ground state to excited state is you shine in light. So an atom in the ground state can absorb a photon and go up to the excited state. And of course, this is just 2 electronic states out of a huge, actually infinite number of bound states of hydrogen. But what makes an atom, a generic atom, kind of interesting for interactions with light, as compared to just a kind of mirror, is that it's a very anharmonic system. So when you go from the ground state to excited state, there's a well-defined transition energy. But the point is that when you take an atomic structure, the atomic energy levels, they're anharmonically spaced. So the energies actually go like kind of 1 over n squared, where n is this kind of principal quantum number here. And so in practice, if you shine in a laser that's resonant with G to E, there's not going to be another transition higher up that's also resonant with that same laser. So in practice, once the atom climbs from G to E, it basically stops. It can't continue climbing up the ladder. So what that means from a kind of minimal model standpoint is that your atom is like a 2-level or pseudo-spin 1/2 system. So if you were to take a laser, which is kind of classical laser light, or sorry, classical light, or coherent state more properly, once you go up to E, of course, the way that an atom goes back down to G is by emitting a single quantized photon, so a Fock state. And it turns out that even though you shine in classical laser light, what you get out, this kind of single photon Fock state, that's already a quantum state of light. So it has certain properties that you can never understand or model from, for example, classical probability distributions. Okay, so this shows you that this very basic system of a single atom is already capable of generating non-classical states of light, and then these non-classical states of light could, in principle, be useful for things like quantum information processing. So aside from generating non-classical states of light, or single photons, you can also, even at a pictorial, cartoonish level, imagine other things that you could do with atom-light interfaces. So another big application, or class of applications, is nonlinear optics at the single photon level. So nonlinear optics is about getting pulses of light to interact with each other. So it's been a dream, I guess, for a long time in classical optics to maybe build something like a photonic transistor rather than an electronic one. And so a single photon level nonlinear optical system would be one where single photons, individual photons, can interact with each other quite strongly. So that would allow you to build, for example, an optical transistor that switches the propagation of another field at the level of single photons. You can also imagine building up photon-photon gates, entangling gates between single photons for quantum computing, et cetera. And the kind of cartoonish picture of how that works is pretty simple. So again, the atom is a two-level system, which means you can only put in one single excitation at a time. So for example, maybe I could design a system where I shine in one photon, the atom absorbs that photon and sends it going backwards in the reflected direction. But then if I shine in two photons, the atom can't possibly interact with those two photons or absorb those two photons at the same time. So then it's quite likely that these two photons would get transmitted instead. Okay, so one gets reflected, two get transmitted. That's a basic example of a nonlinear optical process, and in fact, that has some kind of entangling properties that you can exploit. Another kind of big application is a quantum memory for light. It's kind of well accepted that if you want to send quantum information over long distances, like qubits, the best way to do that is photons, because they travel fast. They can propagate for many kilometers, potentially, without being absorbed. But then, if you want to kind of harness that information and process it, you don't want your qubits flying at the speed of light. Okay? So what you would like to do, presumably, is find some way to coherently convert, or find some unitary map that allows you to take quantum information, for example, encoded in qubits of light, in polarization, for example, and convert that into some kind of collective atomic wave function. So you want to kind of transfer photonic information to atomic information. And you want to be able to do that back and forth. So that would be something like a kind of coherent quantum hard drive, if you want. Atom-light interfaces are also very useful in quantum metrology and sensing. If you want a kind of cartoonish view of that, for example, if you had a kind of either static or time-varying magnetic fields, your atomic levels are usually sensitive to that. So a magnetic field might cause your excited state energy, or the difference between ground and excited state energies, to oscillate as a function of time. So your effective resonance frequency of that optical transition is changing. And then that kind of time-dependent change in the optical resonance frequency, you could try to monitor by the scattering of light. Okay? So if you can see some change imprinted onto the light that you send in, you might try to go back and infer what the magnetic field was. So that's a very basic example of a magnetometer that's based on atoms. You can enhance that magnetometer further by using then a collection of atoms. Thereby you gain signal-to-noise ratio. And then what you can actually do at the same time is even use the light. So before you, so not only use the light to measure magnetic fields, but before you measure the magnetic field, you might use the light to entangle the atoms together into some entangled state, like a squeeze state, which has a higher sensitivity to whatever you want to measure. Okay, so those are all the things, or well, not all the things. Some of the paradigmatic applications that people would like to use atom-light interfaces for, and at least to some version, to some degree of fidelity, people are already able to implement things like that in the lab today. So at the risk of kind of oversimplifying things, maybe a general rule is that in the lab we can already do all the things that I talked about now, but maybe not to the level of perfection that we would like. So errors are too big, et cetera. And then it's kind of worth asking, well, why is it so hard? And one way to kind of understand why it's so hard is actually just to think about the basic building blocks of all those atom-light interfaces. If I just start with one atom, and I shine in one photon, what is actually the kind of interaction efficiency that I can achieve? And it turns out that that efficiency for a single atom and a single photon is intrinsically going to be low, just kind of dictated by basic laws of nature. So if we talk about interaction efficiency, we have to kind of make a more precise definition. And one way you can define efficiency is through collection efficiency. So for example, imagine that I have an atom which is excited. So it'll emit a single photon, which is non-classical. But the spatial pattern in which emits that photon, you can understand by just classical optics. So in particular, it emits light in the same pattern that a radiating point dipole would in classical optics. Okay, so you get this kind of famous lobe radiation pattern. Okay, so it's not completely isotropic, but you see that essentially a point-like atom essentially emits light into 4 pi. And the problem in experimental optics is that we don't know how to catch light in 4 pi. Okay, so not with realistic lenses, et cetera. So what we can really only do is collect light into kind of nice modes. So in lab, for example, we know how to generate focused Gaussian beams and collect light into Gaussian modes. And then the problem is simply, the collection efficiency problem is simply the fact that a Gaussian mode and this kind of 4 pi dipole radiation pattern are not the same. You don't get a kind of unit overlap between those two modes. So in particular, while a dipole emits into 4 pi, if you can generate a Gaussian beam, Gaussian beam for our purposes is just some kind of focused beam, where at the kind of focal plane, you have a kind of effective area that's given by the beam waist squared. Okay, and if you remember from kind of basic. Sorry, I'm not sure what happened. I think the Zoom might have froze, or.
Zoom is out of, because I can see here
Yeah, I saw they're just frozen. Yeah, I think it froze and stopped.
Okay, let's try it again. It could be the internet. Yeah, it's the internet.
maybe you can connect it directly to the LTE.
Foi.
Okay, thanks.
Go ahead.
All right.
Sorry, guys.
No problem. Okay. So you might remember from classical optics that the tighter you focus a Gaussian beam, so in other words, the smaller W squared is, the faster the beam diverges away from the focal plane. Okay, so in fact, if you focus on the focal plane to an area W squared, then the solid angle that's subtended by the Gaussian beam, as you look away in the far field, is actually lambda squared over W squared. So then the kind of fraction of the energy that you catch from this dipole pattern is basically this solid angle of the Gaussian mode divided by 4 pi. And so then up to kind of proportionality constants, your collection efficiency is given by the wavelength of the transition squared divided by the beam area. So it's a very simple result. You see it doesn't depend on any microscopic details of the atom like the Bohr radius, et cetera. It just only depends on the resonant wavelength of the transition itself. So then it turns out that you can also understand this problem of efficiency in a complementary way, or essentially by time reversal. Okay, so if you have an excited atom and it emits outward into this Gaussian beam with some efficiency of lambda squared over A, then if you play the movie backwards, that's also a valid physical process. And so it turns out that that same efficiency, that lambda squared over A, that also dictates the probability that if you send in a photon in that Gaussian mode, that's the probability that that one photon will excite or be absorbed by that single atom in the first place. Okay? So again, the scattering probability or efficiency is also lambda squared over A. And then if you really kind of try to build this experiment, the record efficiency that you get with single atoms in free space is about 10%. Okay? So if you could somehow make that number 100%, then in principle you could do every single application arbitrarily well or arbitrarily perfectly. But the problem is that it's not 100%, but 10% instead. Okay? So that's actually a well-known problem in quantum optics. And people have already spent decades trying to fix that problem. So you might have heard of one experimental paradigm called cavity QED, where you put one atom between two very good mirrors, and so the photon comes back and hits the atom over and over again. There's an alternative approach which is just instead of using mirrors, to use many atoms. And then the idea is that you enhance the efficiency through so-called collective enhancement in quantum optics jargon. And so simply the idea is that, well, if a single atom interacts with a probability lambda squared over A, now you have a large atom number, so that atom number multiplies the probability of interaction. And then in quantum optics language, this kind of combination of parameters, lambda squared over A times atom number, that's known as the optical depth of your atomic medium. And again, this kind of optical depth of this probability has a complementary viewpoint. So in particular, you can also think of it as, if I have one excitation, so I have one excited atom, but shared among the n atoms in the system, then if I prepare a certain superposition, so atom J is in an excited state with some superposition e to the, or with some local phase, e to the I k dot r, then what it means is that single excitation can emit efficiently into this kind of quasi-one-dimensional light mode, this Gaussian beam, at a rate that's enhanced by the atom number. So again, it's only one excitation, but through essentially a kind of constructive interference effect, you can get that one excitation to emit into your preferred mode of collection more efficiently. Okay? Whereas in the other directions, it's assumed that on average there's no collective enhancement. So in the rest of 4 pi, a single atom would still emit a photon at a fixed rate gamma naught, which does not depend on atom number, atom density. It's exactly the same rate that a single isolated atom would emit into 4 pi. So then you can also define the optical depth as basically that branching ratio of kind of good information which is collected versus the information which is lost. Okay? So once you view this optical depth as a branching ratio of information, of quantum information, then it kind of makes sense that that optical depth should set a fundamental limit on the error of any application that you want to carry out. So here's a kind of cartoonish version, but if you want to get some sense of the physics, it's a completely classical optics phenomenon. So even if I were to take classical radiating dipoles and just assign them a phase, e to the ik dot r, depending on their position, if you were to calculate the total scattered field or emitted field from that system, you'd find that in the direction set by k, you would get this kind of collective enhancement or constructive interference of emission into your preferred direction. Okay. So again, the optical depth, just to summarize, this parameter of optical depth is basically the main figure of merit that dictates fundamentally how well you can carry out any application. So you can find millions of examples of that in literature. Here's actually a review paper on just kind of general applications involving light and atomic ensembles. In the first paragraph, they say the requirement that the optical depth be large is the most significant requirement for anything known up to now. If you want a kind of more specific example of that, here's a kind of paper where they study this quantum memory application or photon storage. And you can imagine that in the lab, if you want to actually carry out a quantum memory, there's actually different paradigms or different protocols that you can choose from. And one of the elegant conclusions of this theory paper was to point out that no matter what approach you take, as long as you properly optimize your experiment, you'll get the same maximum efficiency in the end, which only depends on the optical depth of the medium. And what they found is that asymptotically, that error scales like 5.8 divided by optical depth. Okay. So that's kind of abstract scaling, and now you can ask, well, what does that actually look like in an experiment? So here's actually a close to state-of-the-art quantum memory for photon qubits performed by Julien Laurent's group in Paris a few years ago. And so what they're studying here is the memory efficiency on the vertical axis. So efficiency is just 1 minus the error as a function of optical depth. So they see that at first when you increase optical depth, indeed the efficiency increases according to what you theoretically expect. Now, optical depth is just proportional to the number of atoms. It's not like the number of atoms in the universe is really a limited resource. So of course you can just crank up the atom number more and more. And what you find is that at some point the efficiency doesn't get better anymore, but it starts to go down. And so there's kind of two take-home messages associated with this plot here. So on one hand, as you start to crank up the atom number, the fundamental error shrinks too slowly as a function of optical depth. And then finally, when you increase the optical depth too much, when you have too many atoms, you start to hit other technical errors. So basically, it's just hard to use a very large number of atoms coherently in an experiment. Okay, so at some point, you hit technical rather than fundamental problems. Okay, so in this experiment, the best error they got was still around 30%. For quantum memories, they've, I think in more recent years, brought the error more down to kind of 15% level. But certainly, we're not at the kind of 1% or fraction of a percent level that we might like for quantum technologies. There's another application of photon-photon entangling gate. So here, let me again just kind of present the big picture. And I'll give a more detailed explanation of how this protocol works later. So a typical photon-photon gate might look like the following. You first shine in a first photon, and you do a quantum memory. So you try to convert that photon into an atomic excitation. So you brought one atom in this ensemble from the ground state to an excited state, and in particular to some high-lying Rydberg level. Now, if it's in this Rydberg level, and that error will be kind of 5.8 divided by optical depth. And then the point is that once the atom is in this high-lying Rydberg level, it exerts very strong interactions on all the atoms around it. So it can actually modify the optical response or refractive index, if you will, not of just that one atom, but of some kind of macroscopic region around it. So then you shine in your second photon, and then the second photon basically sees the effect of the first photon through this Rydberg modified region. So it propagates through a different refractive index over a non-trivial distance. And then if you tune that correctly, you might kind of, for example, engineer that second photon picks up an extra pi phase shift, but only conditioned on the first photon being there. So that the fact that it's conditioned on the first photon makes it entangling. And again, the best gate, has an error that scales depending on the optical depth, not of the entire region, but actually just of this kind of blockaded region here. Okay, so this is just to kind of illustrate concretely that indeed optical depth somehow seems to pop up at any time you seriously analyze the errors. The main point, though, is that aside from, again, abstract scalings, the current state-of-the-art photon-photon entangling gate has an error of about 60%, okay, dominated by photon loss. So you try entangling two photons, and around 60% of the time, at least one of the photons does not come out. And that number there is very telling. Okay, so on one hand, that's why you never hear about atom-light interfaces as being a competitive platform for quantum computing yet. Right? There's no companies built on atom-light interactions for quantum computers in the same way that you have, for example, companies based on ion traps, superconducting qubits, et cetera. That same number here, so this is basically you can think of as a building block, right, to build strongly correlated or interesting quantum states of light and matter. So if your building block already has an error of 60%, it makes it very implausible that any kind of many-body interesting stuff would come out, right? And that's kind of one reason, I think, historically, why words like, many fancy words like many-body emergent phenomena are not associated with quantum optics. It's very hard in these systems to generate highly quantum states in the first place. Okay, so that really, so then really the big question is, can we find a way to do better? And part of the context of that is that of course there have been exciting experimental developments, but these are not kind of particularly new ideas. People have had at least a couple of decades to work on these, and the errors seem to be kind of slowly improving as a function of time. But it's hard to see kind of if we keep just pushing on this, that we'll all of a sudden go from 60% error to 1%, okay?
So this enhancement is because you have readback atoms here, right?
Right.
Because you have readback interaction. In principle, we could be do this using neutral atoms, not exciting to read back, and putting it closer, maybe, to make the interaction strong, maybe sub-length interaction.
Yeah, so if I understand your question correctly, so in one of my very first slides, I said that you already get a photon-photon interaction or some nonlinearity because an individual atom is a two-level system, right? So if you can somehow force two photons to hit the same atom at the same time, in principle, that could give you a lot of entanglement. So here I'm actually showing something different, right? Because I'm exciting one atom, but then I'm utilizing a different effect of a Rydberg atom interaction to somehow change the optical properties of many atoms. And it turns out that, at least when we talk about atomic ensembles, this is the only demonstrated way so far to get to that kind of single photon entangling level. The problem is really that if it was not a Rydberg level, so if I just had this one atom excited and then I try to shine in another photon, that photon would somehow would have to find a way to hit that one atom in the first place. And that goes back to my kind of interaction efficiency calculation. So the interaction efficiency is lambda squared over A. So there's only a really small probability that that one photon would manage to find this one excited atom in the first place. So that's why you need this one atom to really kind of create a macroscopic effect.
Okay, so it's because you have readback interaction, not because you have a blockade ratio, something like that.
Oh, so they're the same thing. Yeah. So I'm sorry. Here I'm just kind of leaving it as a cartoonish level. I will talk about more concretely what a Rydberg atom is, what a Rydberg interaction is, and how you can use that for nonlinear optics in a maybe third or fourth lecture. Sorry, there's.
So whenever we have, like, say, those two photons, like, interacting with this one atom, then, like, it only works because we have a nonlinear sort of, like, energy level spacing, like, non-harmonic?
Exactly.
Okay, I see. And then, like, then do people use it in practice, or, like, there are some other, like, issues to this? So for instance, like, I don't know, companies like, say, PsiQuantum, is it like the way they're doing stuff, or?
Right. So I think there's maybe two distinct questions, which I can try to answer separately. So it's a bit subtle, but it turns out if you don't want to do a photon-photon entangling gate, a two-level atom is actually not very good. So even if I can crank that efficiency up to 100%, it's a little bit complicated to use a two-level atom. And the issue is really due to kind of time bandwidth constraints. So basically, you can imagine the following: like when I shine in two photons, I get to choose how long they are in time. If I make them very long in time, and the time scale you have to compare it to is the natural spontaneous emission time of the atom. So that's the kind of memory time that the atom really knows that 1 versus 2 is hitting it. So if I shine in very long photons in time, most likely they don't even hit the atom at the same time from the atomic perspective. If I then make the pulses too short in time, then each pulse has a huge frequency bandwidth. And then you have the problem that some frequency components are too far off resonant that the atom can't interact efficiently, et cetera. So then there's this subtlety that actually a two-level atom is not super nice. The better way to do it is somehow use a three-level atom, which I think I'll talk about in a few lectures. And then you brought up the separate question of, okay, if I do want to use a photon somehow for quantum computing, how would I do it? The scheme that seems to be pursued so far is not based on photon entangling gates, so kind of what I would say kind of circuit-based or deterministic interactions, but more based on measurement. So measurement itself, if it's projective, can create entanglement. And so there's this whole field of, I guess, what we might call linear optics-based quantum computing, where as long as you can generate kind of single photons and shine them as beam splitters and do measurements, in principle, that's also sufficient, or that's in principle one possible way to do quantum computing. And so then the resources you need for that, you need single photon sources, which atoms can provide, but you don't really need to build up these kind of, if you want, deterministic photon-photon interactions. Okay. So that's really what the rest of the lectures are going to be about. Like, how can we do better, much better? And so before we can answer that question, I think it actually makes sense to ask, dig a little bit more deeply. How do we arrive at these physical conclusions in the first place, and what's the underlying theory? So at the beginning, I told you this kind of problem of a single atom and a single photon. I told you that there's this interaction efficiency, which is lambda squared over A. Turns out that that is exactly solvable. That's 100% true. But then I went from one atom to 100, 10,000, or 1,000, 10,000, a million. Okay? And depending on your background, so if you didn't study quantum optics, you might think of atom-light interactions or quantum electrodynamics as being this very fundamental thing. So maybe we had a fundamental underlying theory for it. But then if you just kind of think through it, you would see that it's not that simple. So if I wanted to really have a full microscopic quantum theory of light interacting with an ensemble of atoms, I would need to account for the fact that in a real experiment, there could easily be 10,000 atoms. And if each one is a two-level system, then I'm living in a Hilbert space of 2 to the 10,000. I also have the fact that the atoms they're sitting somewhere in space. Those atoms could be moving around. I don't necessarily know what those positions are. And that's just the atoms. And then when I shine in propagating fields, that's actually a continuum of photon modes. So it can have any frequency, direction, photon number. That's an infinite dimensional Hilbert space. So then when you look at these two things combined, it's kind of pretty clear that you're not going to be solving that problem exactly. Okay. So then what did quantum optics people do? Here I'll kind of present a cartoonish version of effectively what our quantum optics textbooks encode. And then in the lectures, I'll try to follow that up more concretely with real Hamiltonians and master equations. But in a kind of nutshell, our approach to quantum optics with atoms very much follows our approach to macroscopic classical electrodynamics. So for example, if I took a piece of glass, So glass is actually amorphous. So there's 10 to the 23rd degrees of freedom. No two pieces of glass are the same. And then, if you were to look at it that way, you would say, well, microscopically, classical optics is a completely impossible problem. And the way we get around that is basically just to kind of say, almost by fiat, that, well, even though there's the kind of microscopic degrees of freedom, when we care about macroscopic optical response, we can somehow do a kind of separation of scales, and then invoke that, at least we believe, that the response of the medium to light is encoded in a single number, which is the refractive index. Okay? So as long as I know the index and I know the shape of, in this case, the prism, I can then predict the optical functionality of that system. And then it turns out in our standard formulations of quantum optics, it's exactly the same idea. So although you in principle have a granular set of atoms, you say or you simply hope that that granularity doesn't matter. You can say I can basically smooth over the granularity, and in this case, replace the atoms with a smooth quantum polarizable medium, which in itself is a kind of quantum field, if you want. Okay. So that's really the simple story. Our standard picture of quantum optics is that of a macroscopically smooth medium. And so then it's kind of clear that what's left out really is the granularity of atoms, the fact that they're point-like scatters, which have to sit somewhere. Okay? And so then even from classical optics, you can start to guess what you're throwing out in the standard theory, which is multiple scattering and wave interference. And so that's not a particularly deep statement. Anyone in classical optics knows that if you have point-like scatters, you can have multiple scattering and so on. But what makes the problem maybe especially kind of rich for atoms is that you expect that this kind of multiple scattering might be strong or even non-perturbative once the distance between atoms becomes sub-wavelength. So the picture is that each atom has a scattering cross-section that's kind of lambda in size. So once the distance between atoms is sub-lambda, then these scattering cross-sections start to overlap with one another. And then you can kind of imagine that your naive approach of calculating scattering would start to break down. Okay. So that's kind of true at a general level. If we go back to this message of branching ratio of information and optical depth, the point is, again, if you want to build an efficient interface, you want to basically collect 100% of the light and have none of the light emitted into 4 pi or into directions you can't catch. And the point is that once you say that everything is multiple scattering and wave interference, you realize that it's not only true for this kind of preferred direction of emission, but it's also true for the 4 pi emission. Okay? So in particular, this assumption that quantum optics textbooks just kind of, again, put in by fiat, that if you have an excited atom, it's going to emit into 4 pi at a fixed rate of a gamma naught, which you can never change, that cannot be true. Right? Because if you accept that the emission of energy in the far field contains wave interference effects, then from the atomic point of view, that means that the dissipation has to look correlated rather than independent. So that's going to be basically the main theme of these lectures, to realize on one hand that the problem of light emission truly is a correlated dissipation problem, quantum correlated dissipation problem. And then, the kind of big picture is, well, if you realize that, can you somehow exploit wave interference in your quantum protocols? And again, the kind of cartoonish picture, which I think one can already start to take away, is something like the following. So in the quantum optics textbooks, what you're really only trying to exploit is collective emission or constructive interference in the forward direction, or the direction that you can catch, while you assume that the rest of emission into 4 pi is uncontrollable. And the statement is that actually, well, if you realize that 4 pi in principle depends on wave interference as well, maybe you can start putting down atoms in very particular positions, for example, using an optical lattice or tweezers, and then kind of shape the 4 pi emission through interference to be whatever you want. And in particular, if you're lucky, which we find that we will be, maybe you can even make the 4 pi emission get suppressed exponentially in the atom number. So now if I try to construct a branching ratio of information of good over bad, my actually good emission is actually pretty wimpy because it's only growing linearly with atomic number. Whereas if I can make the kind of bad stuff get suppressed exponentially, then all of a sudden I can exponentially beat the error bounds that the textbooks told me about. And that I find really surprising. So this is a very kind of personal story or journey, if you want. When I learned quantum optics in textbooks, no one ever told me that those equations had some kind of dirt that people were sweeping under the rug. People just presented as, well, that's the absolute truth. And it really didn't kind of strike me until a few years ago that actually this somehow had to be the real answer, even if you just take kind of basic classical optics considerations into account. And the first moment we found that we can actually do exponentially better in a particular application, a quantum memory, I was completely stunned. Okay, I was like, all these years I learned quantum optics and I thought I knew everything. All of a sudden now I know nothing again. It's really, really been a kind of fascinating journey to kind of rethink quantum optics, what is actually true, and what is the real balance of quantum atom-light interactions. Okay? So this concept here is what we call selective radiance. I gave you actually this kind of paper here for background reading if you're interested. At the same time, if you realize that all of emission is collective, then instead of trying to kind of get light to emit efficiently into a certain direction, you might actually find kind of manifolds in your Hilbert space, which are entirely subradiant, where basically destructive interference prevents those excitations from ever getting out. And then, if your excitations can basically live forever, then any small coherent interaction that you have can accumulate, and eventually you might be able to build up some interesting strongly correlated state. Okay, so that's where kind of the notions of now emergent phenomena and quantum antibody phenomena might start to become plausible. Okay? So again, what I kind of showed here in the slides is just meant to provide a big picture overview, but ideas like this of really getting kind of efficient interactions between atoms and light, maybe exponentially more efficient than what the textbook said was possible, or shutting off dissipation altogether and allowing coherent interactions to build up. That makes this kind of field of quantum optics with kind of well-positioned atoms or arrays a rapidly growing theoretical and experimental fields. Okay, so with that, the goals, the kind of overarching goals of the lectures are the following. So first, we have to figure out how to develop a fundamental theory that builds in non-perturbative multiple scattering of light and wave interference into our atom-light interactions. And then I'd basically like to discuss some of the consequences. So on one hand, I'll try to present a couple of concrete protocols of quantum applications where you can have either polynomial or exponentially better error bounds compared to what the textbooks said was possible. I'll try to give examples of surprising phenomena, emergent phenomena, if you will, that pop up, that arise specifically driven by granularity and interference, which just can't arise even in principle within a conventional theory, simply because the conventional theory is too incorrect or started from too bad of a hypothesis. And then, actually the final message I hope to leave you with is that this is still a very new and incomplete field. So, again, a few years ago, I thought that I knew everything about quantum optics. Then I realized I knew nothing because, how can I be exponentially wrong, or how can a textbook be exponentially wrong? And I'm still very much interested in finding the real answer. So I do believe that, the space of possibilities of atoms and light is much broader, maybe exponentially bigger than what we currently know. But a lot of that kind of frontier, the uncertainty, is really in this kind of many-body non-equilibrium regime. So that's not a field that I ever learned about as a graduate student. But I think those ideas will be key to really kind of shaping this field of atom-light interactions in the near future. Okay. So again, that kind of completes the kind of big picture perspective. I don't know if you have any questions, or if not, then I'll start going to the blackboard and start developing these ideas more concretely.
So just a general comment, like, this is very relevant to atoms, like single-trapped atoms, but also, like, is it something that people are thinking about also, like, in solid-state platforms? or stuff like this?
People are thinking about it. I think you can ask different versions of the question, but maybe the kind of most technologically relevant one is maybe I would like to start positioning atoms exactly where I want to start exploiting this kind of selective radiance and maybe get this exponential gain in errors. So then in terms of solid state emitters, so there are certainly very good solid state emitters, quantum dots, color centers in diamond, et cetera. The problem though is that I think, well, at least I don't know of any particular system where you can really build arrays which are really homogeneous enough at will. So as a concrete example, silicon vacancy centers in diamond and germanium vacancy centers, they are actually pretty close to this kind of ideal two-level system when we talk about atom-light interactions. And then the way you position them in diamond is essentially by ion beam implantation. So you can try to say, I'm going to start bombarding my diamond with impurity ions until a color center spontaneously forms. And then it turns out the kind of the spatial uncertainty when you implant is about, I think, in the 5 to 10 nanometer range. So that's pretty good. The problem, though, is it's a Poissonian process. So you can't really say, so you bombard, and you might generate 0, you might generate 1, or you could generate 2 and 3. And so the problem then is really with this kind of Poissonian distribution, because what you really want, presumably for quantum optics, is exactly one atom every given distance. So that's kind of one specific example where color centers diamonds seem to satisfy some of the ingredients, but then not all of them, at least with current technology.
So if you mind summarizing again, like how do we get this exponential suppression in one direction? Like, is it, because I see that two components should be granularity and interference, but like, I mean, I see more of interference, for instance, for this like subradiance and so, but like, how does granularity come in?
Right, so I'll get into that more in the lectures, but maybe if I were to draw a kind of everyday example, you can think of these telescope arrays. So when you look into space, some of the best telescopes today are not individual telescopes, but actually, telescope or antenna arrays. So it's exactly the same idea in reverse. So by creating these arrays, you can make yourself very sensitive. So these arrays receive information, but you could imagine playing the movie backwards as well. So if they were to kind of launch waves themselves, you can imagine that they can make it very collimated, right? Where it can essentially get all the energy emitted in your preferred direction and none of the emission into directions you don't want. So it's the same idea with atoms, just at a much smaller scale.
When do you run the simulation? What type of field do you consider? I think about laser or variation for type of laser beam, like Laguerre-Gauss or Gaussian beam. What do you use? And you media too.
Okay, yeah, so again, I think it'll be more clear in the actual lectures, but to give kind of a preview, when we shine in light, there's kind of, I guess, two things we can decide. One is like the spatial mode, so Gaussian, Laguerre-Gauss, a plane wave, whatever you want. So if our goal is to really kind of create efficient atom-light interfaces, the main constraint is we have to choose a mode that's realistic. So for example, we might launch in a Gaussian mode, or say we have a single photon in a Gaussian mode that we're trying to store. It doesn't have to be a Gaussian mode per se, but it has to be kind of one that people can realistically generate and collect in the lab. The other thing we can talk about when we shine in light is the kind of statistics of it. So we can say it's a coherent state or classical laser light. That turns out to be very efficient to build into our to this formalism when we calculate multiple scattering. In principle, you could also send in Fock states as well, or I guess any other non-classical state that you want. It turns out, though, that the complexity of encoding that, so a single photon Fock state or a few photon Fock state, that's pretty easy to kind of encode into the formulas itself. If you give me some huge, like 100 photon entangled state, somehow you can imagine that the source that created that was also already some many-body complicated system in the first place. So even though it's not direct, somehow it's like when you simulate these atoms with some fancy source of light coming in, the ingredients that you need to kind of create that source from the beginning, you would have to somehow implicitly include in your Hilbert space of the system, and that can make the simulation very complex.
Yeah. Thank you.
Okay, so I guess with that, I'll switch to the Blackboard. So what I'd like to do now is introduce a kind of minimal model of atom-light interactions, or atoms interacting with a continuum of photon modes. And this model is known as basically the one-dimensional chiral waveguide. So honestly, it's a pretty kind of, maybe if you, at first glance, it might look like a pretty peculiar example, okay? Because we're not, I mean, in real life, we of course live in 3 dimensions, not one. We have the so-called chiral interaction, which I'll introduce, which somehow seems a little bit non-natural as well. So it turns out that actually in labs today, we can generate this Hamiltonian with realistic platforms, at least to some extent. So it does turn out to have some kind of physical bearing, which I will also introduce later. But actually, one nice thing about this model is that you can kind of view it as the parent model to build up a lot of the ideas that I described here. Okay. So in particular, I think it's a minimal way to introduce the kind of textbook descriptions of atom-light interactions, but without going through all the kind of complex discussion of what you actually see in a textbook. Okay. So, and at the same time, it's nice because, okay, so right, maybe the points are that it connects to textbook theory. So with a slight modification, you can basically reproduce the kind of wrong model that you find in quantum optics textbooks. This particular model is exactly solvable by something called beta ansatz. So if you're familiar with beta ansatz or have a kind of particular inclination towards mathematical physics, you'll like this as being an exactly solvable or integrable model. If you do work with beta ansatz, you'll probably also agree that beta ansatz, or the fact that it's exactly solvable, is not as good as it sounds. Okay, so despite being exactly solvable, it's usually not feasible for large systems, or in particular large photon number. And it's a special limit. So if I were to kind of break the integrability, if I were to add any random other term to my Hamiltonian, then all of a sudden the beta ansatz kind of disappears. Okay, so. Sorry. So it doesn't generalize. And then, basically for these reasons, despite the fact that this thing is technically exactly solvable, it really sorry. Yeah, so if you know anything about kind of integral models in physics, they're very special. So I give you a Hamiltonian that looks exactly like something. Exactly, right. No, it's very, so it's very, I'll introduce the Hamiltonian in a bit, but then we'll actually do the beta ansatz and just see by construction you can solve it. But for example, when I say it doesn't generalize, so this particular model is of light that only propagates in one direction and interacts with two-level atoms. So if I were to add any other levels, like a three-level atom or two-level atoms plus Rydberg, the beta ansatz would break down. If I were to add, in realistic experiments, that maybe light could also scatter or propagate the other direction, then the beta ansatz would also break down. So yeah, it just doesn't, it doesn't help for more general models of atom-light interactions. These kind of bottlenecks, if you want, also motivate the need for a more general approach. Okay, which is exactly what this kind of spin model, quote unquote, will attempt to do, right? The next thing is, right, so I guess I kind of hinted that, the formulation of atom-light interactions, which allows you to take into account wave interference and so on, it's going to be, the idea will be map the quantum optics problem onto a many-body open dissipative spin model. Okay? And so this kind of 1D chiral waveguide is also nice because it's a very easy example where you can see how to construct that spin model starting from the full atom-light Hamiltonian. So it's easy to construct the spin model and kind of physically understand what the spin model is building in. Okay. So for those reasons, I decided to present this chiral waveguide as the kind of first problem of atom-light interactions. I should say it's very strange. So I only decided to try this this time. This might be the first time in the world that people introduce quantum optics or taught quantum optics starting from the 1D chiral waveguide. But we'll see how it goes, okay? Okay, so the kind of, in pictures, the model looks like the following. I just have some notion of a pipe or a waveguide in 1D that supports propagating fields. The fields will only be propagating, let's say, to the right. So there's no propagation allowed to the left. That's why it's called chiral. We'll assume a simple dispersion. Relation of omega equals ck. Okay, just like in free space, so if there's no atoms or if you just have a free field, it'll propagate at the speed of light without any distortion forever. Maybe one kind of peculiarity is that, we'll take the spectrum to be unbounded, okay? So whereas for real photons, k goes from 0 to infinity. Here I'll actually allow k to extend to minus infinity. That just makes kind of definitions of canonical quantum fields a little bit nicer. For resonant atom-light interactions, that doesn't really matter because the atoms have a resonance frequency. They'll only efficiently talk to photons around that frequency anyway. So exactly how the dispersion looks at the bottom or the top doesn't really matter. Of course, if we want to talk about thermodynamical properties, statistical physics, that doesn't make sense. But that's not the goal here. Okay, so it's a little bit artificial, but sufficient for our purposes. Okay, and finally we have atoms which can sit at some discrete position z1, z2, z3, etc., and interact in a point-like way with photons. Okay, so that's the kind of pictorial model of a 1D chiral waveguide. And then the Hamiltonian for the system is the following. So we'll have a term that describes free photons, so AK dagger AK. I should say here that in the following we'll set h bar and the speed of light equal to 1. So this is like the free term, and then we'll also have an interaction term. So I'll define, I'll parameterize the interaction by a rate gamma 1D. I'll describe what that is in just a second. So the form of the interaction will be one where any atom I can go from the ground state to the excited state physically by absorbing or annihilating a photon in mode K. Plus the Hermitian conjugate. Okay. So in quantum optics, instead of using the usual Pauli matrices to represent two-level systems, we instead like to write things this way. If we have an operator sigma alpha beta, that's just alpha, the ket alpha times the bra beta, and then alpha and beta can be either E or G, okay? So sigma EG basically means it's a raising operator. It acts on an atom, takes the atom from the ground state up to the excited state. Creation operator, right, for the spins. Or spin raising operator, if you want. Okay, and then this rate, gamma 1D, what we'll find very shortly is it describes the rate. So if you only had one atom coupled to the waveguide and it was in the excited state, it turns out this rate, gamma 1D, is exactly the rate that this excited atom decays into the ground state and emits one photon into the waveguide. Maybe one more note. So here I define the free photon dispersion relation. In principle, I could also add, if I wanted to be kind of proper, I could add a term like this, where omega naught is my excited state energy. So in other words, omega naught describes the resonant photon that I would have to absorb to go from the ground state to the excited state. Okay. What I'll simply do, though, is I'll ignore this term here. And the reason that you can do that is because I have an infinite dispersion relation. Okay, so if my dispersion relation of omega of k really goes from minus infinity to plus infinity, physically my atoms would couple to photons near some resonance frequency omega naught. But if there's no bottom and no top, I could set omega naught to be anything that I want. In particular, I could set it at the origin, and it doesn't really change any physical consequences. Okay. Okay, so I just kind of presented this Hamiltonian by fiat. But maybe the first thing you can do is just to check that it produces reasonable equations of motion, so to kind of justify as a reasonable starting point for a minimal model. So the first thing you can do is you can define. So what we'll see now is see that this Hamiltonian produces reasonable equations of motion. So to that end, the first thing we can do is, well, in classical optics or in Maxwell's equations, we're more used to defining and thinking about fields in position space. Okay, so we can kind of adapt a similar approach here. I can define a photon annihilation operator in real space, which is just the Fourier transform of the annihilation operators in K-space. It's straightforward to show that with this definition, you can rewrite this same Hamiltonian in position space in the following way. So this term here now says that, okay, in real space, an atom I can go from the ground state to excited state by absorbing or annihilating a photon at its position Zi, or vice versa. And then, if we recall that in the Heisenberg picture, the time evolution of any operator O is given by the commutator of the Hamiltonian and the operator itself. Then it's a pretty straightforward exercise to show that if you write down the Heisenberg equation for the field, you get the following. So this is something like our kind of one-dimensional version of a Maxwell equation. So if we didn't have any atoms, then the right side would be 0. So then we just get a kind of normal free wave equation for the field. So del t plus del z of A is 0. And then what you see is that when I have atoms, they basically act as point-like sources for my field. Okay, so on one hand, excited atoms could source the field and generate photons from the vacuum, and kind of vice versa. I won't write down the equation explicitly, but if I were to write down equations of motion for the atoms, they would be driven by the field. Okay, so if you want, this is kind of a reasonable. So if you didn't know anything about quantum electrodynamics, but you just wanted to kind of take reasonable guesses of a good quantum wave equation, this is probably the first thing that you would kind of write down. Okay, so something like this is certainly true in the classical domain. The point is now we get an equation that has very similar structure in the quantum domain. And if you want, if you accept this as a reasonable minimal model of atoms and light, then you can also accept, by kind of working backwards, that this is the kind of correct starting Hamiltonian for such a description. Okay. Any questions on this?
I'm not sure how to interpret this term with like sigma dash. So this one is like written in a Heisenberg picture, right? So I should just think of it as like some wiggling, like some exponentials, like to this alpha beta.
Sorry, I'm not sure which term you're referring to.
So the one on the middle board and
here?
Yeah, so below the one in the bracket.
This one?
No, the one below, yes. So then there's like this sigma with a dash. So is it just like sigma written in a Heisenberg picture and then like I'm kind of like also time evolving it?
Yeah, exactly. So so
okay.
This is right. Everything here is in the Heisenberg.
Okay, I see.
Picture.
I see. Okay,
right.
cool, thanks.
At the moment, we are considering only purely coherent processes, like gamma 1D is not the spontaneous emission rate, or
It is. So So I haven't shown it yet. So actually, probably at the beginning of next time, I'll explicitly show it. Maybe I'm not sure if this is what you're asked. So maybe I'll try to reinterpret what you're asking. You can tell me if this gets to the point. So if I were to look at the atom alone, so if I were to kind of trace out the fields, then yeah, my claim is that gamma 1D is the rate that the excited state population would exponentially decay physically because you emit a photon. So here what I'm simply doing is, so in that picture, I'm treating my photons as a bath and my atoms as a system, so then I get an open system or dissipative dynamics. Here I'm just simply writing a Hamiltonian where my system and bath are all included as a new, bigger system. So everything is unitary. I would still be able to kind of capture correctly that the excited atom does exponentially lose population, but physically because it's doing a unitary transformation where that excitation gets mapped to an outgoing photon. So does that?
Yeah, it answers to
Okay.
my questions. Thank you.
Okay, so so maybe the next thing we can do is again just to show kind of how things are calculated in principle and to get a little bit of intuition. We can calculate a relatively simple dynamical problem of single photon scattering. Sorry, maybe one thing I should have said at the beginning is, so in the school there were several words: emergent phenomena, many body, etc. There was also the word non-equilibrium. So actually, at least in that respect, quantum optics people are very good about doing non-equilibrium calculations. And the reason is because the whole interest is shining in light in the first place, right? So the ground state of an atom-light interaction system is completely trivial. The photons would be in vacuum. All the atoms would be in the ground state. If you want a classical analogy, if I have a prism but I don't shine in light, it doesn't do anything, right? So the only interest in optics is to shine in light, kick the system out of equilibrium, and modify the light that comes out, okay? So you can view this kind of single photon scattering as the most basic example of a non-equilibrium calculation, if you want to say it that way, although there's nothing kind of many-body about it, okay? So this is kind of so if we call, so single photon means basically I have one excitation or one photon coming in. You can also view the single photon scattering as the beta ansatz calculation in the single excitation manifold. Okay? So if you're not familiar with beta ansatz a priori, don't worry. You'll see that it doesn't mean any kind of, it doesn't mean anything scary in particular, right? It just means that there's some way to solve this problem exactly, right? And so physically, the thing that we'll want to study is, we imagine we have a single photon in some quasi eigenstate, so a wave packet where the K is very well defined, coming in from far away, it hits a single atom. So sorry, single photon scattering, I should say single atom as well. Okay. So it'll eventually come in, scatter off the atom, and then we want to kind of figure out what comes out. Okay, so can we solve that quantum mechanical scattering problem? Okay. So what we'll want to do is calculate eigenstates. So what we'll want to do is see that we can solve a problem like this. Right? Where this K, I'll kind of, just for this equation here, kind of put it in quotes. Because K will not be just a free photon. So if it's a free photon, this K clearly would have the meaning of being a plane wave, e to the I kz. It's kind of intuitive that a pure plane wave e to the I kz cannot be an eigenstate of the full problem, right? Because the atom has to do something to that photon in the first place. So this K here is kind of meant to label a kind of quasi wave vector, but it can't, right, a true plane wave cannot be the eigenstate of this entire problem. So K is just some kind of abstract label, if you want, not necessarily pure wave vector. Right? So then the first thing we can do is take an ansatz, which you can easily generalize to more excitations. So if I have one excitation, the most general wave function I can write down is I can either have that one excitation sit on the atom. So, sorry, here I'll denote 0 as the total ground state of the entire system. So both my atom is in the ground state and my field is in the vacuum. Okay. So if I only have one excitation, it can either be sitting on the spin itself with some unknown amplitude CE, or it can be sitting in the photonic degrees of freedom. Okay, so I can have a superposition of one atom at position z with some up to now unknown amplitude f of z, right? And the point is simply to show that if we take this general ansatz and plug it into the time-independent Schrödinger equation, we can uniquely solve for CE and this amplitude f of k. Okay, so we'll want to solve for CE. And the position-dependent amplitude of the photon. So maybe in the interest of time, I'll skip a couple of intermediate steps. So I'll simply claim that if you take this equation and plug it into here, it's just like a usual quantum mechanics problem. So then you can kind of separate it into a basis, look at the equations in each basis set, and then what you find are the following. So one equation that you get. Sorry, let me. Is you get a differential equation for this function f. So del f del z minus ek f k of z equals square root of gamma 1d times CE times delta of z. Okay? So the left-hand side is like a normal wave equation, for light, which is kind of normal. And what you see is that the atom, so sorry, I should say that this atom I'll assume is sitting at z equals 0. So then what you see is that, again, the atom kind of acts as a source or a source of discontinuity for the field at the atomic location. Okay? So that's how the interaction of the field with the atom is encoded. And then you can get a second equation for the atom alone, which is the EK CE plus square root of gamma 1d, Fk of 0 is 0. Okay, so if we look at equation 1, away from the atomic position, so then the delta function disappears. We get a pure wave equation, which means that as long as you're not at the atomic position, you must have that Ek is k itself. So in other words, the eigenstates or the eigenenergies of the full interacting problem are the same as the dispersion of just free photons. And then similarly, if you're not at the atomic position, then the field amplitude should be a pure plane wave, e to the ikz. But then it's interrupted at the atomic position. So if you're to the left of the atom, so you have a step function of minus e, then it's e to the ikz. And then generally when you hit the atom, so when you go from the left of the atom to the right, you can experience a discontinuity with some amplitude tk, where tk you can eventually interpret as a transmission coefficient for the atom. All right. So this is generally true. What we don't know is we don't know tk. But if we plug this back into equation 1, and we also solve equation 2. So equation 1 and z equals 0. And equation 2, they allow us to solve for the transmission coefficient and also for CE. So what you find is for the transmission coefficient, is the following, right? So now let's talk about the kind of physical consequences or interpretation. So the first one is that the amplitude of the transmission is always equal to 1. And that's because we have a purely lossless chiral system, where I shine in photons going from left to right. There's no backscattering channel, so the photon can't go anywhere else. It has to continue to the right. The second thing you can plot is actually the phase. So as a function of k, I can plot the angle of the transmission phase. So if I'm very far away, so remember that in this picture here, k equals 0 corresponds to my resonant wave vector. Those are the photons that are resonant with the atomic transition. So if my k is very negative, then my angle of transmission is actually 0, which is to say the atoms are or it doesn't matter whether the atom is there or not. Right? So if I have just empty space, then the transmission coefficient past any given point would be exactly 1. Okay? If I'm shining in light with a k vector much above the resonance frequency, what you find is that the transmission phase is 2 pi, which is also indistinguishable from 0. So again, light, which is very far off resonance, basically doesn't see the atom at all. But then crossing the resonance, you actually get a pi phase shift. Okay, so it's on resonance that the photon actually knows about the atom. And it knows about the atom in the sense that it picks up a non-trivial phase shift scattering past that atomic point. Okay, so this is, you can view as just kind of non-resonant interaction. But then on resonance, the photon knows about the atom through a non-trivial phase shift. So here I explicitly did the calculation for one atom and one photon. But it turns out you can easily generalize the same calculation to one excitation and as many atoms as you want. And the trick is really because the scattering is chiral. Okay, so the photon starts from the left, it passes the atom, it has to go to the right, it has no other choice. And then if you were to see a next atom, again, it has no other choice, right? So essentially the problem factorizes, right? A photon just kind of transmits past each atom one at a time. And there's no possibility of backscattering, which would make the calculation more complicated. Okay? So then it turns out, for n atoms, the transmission the total transmission coefficient, if you want, would just be tk to the nth power, right? So hopefully this gives you a sense that this particular chiral waveguide model is easy to solve. For one excitation, an arbitrary atom number, essentially because of this separability. Right? And again, the fancy name for this historically is it's a version of so-called beta ansatz. Actually, not for the exercise tomorrow, but for the second one, if time allows. We'll actually do the beta ansatz for 2 excitations and n atoms. We'll see that there's some kind of interesting so-called bound state physics there. We'll explore the consequences of it. So you see that in principle it is exactly solvable for 2 excitations, 3, 4. You could try to write down a similar ansatz, but then you can kind of believe that it gets nasty after some point, right? So it's a straightforward procedure. But at some point, even though you can write down an exact answer, it's not really helpful anymore. It's a high-dimensional wave function. If you want to calculate any observable, you have to start calculating high-dimensional overlap integrals, etc. Okay, so that goes to the point here. It's technically exactly solvable, but it's not as good as it sounds. Okay, and for that reason, we really need to find more general approaches to deal with complex problems involving many atoms and many excitations. So I guess that's maybe a good stopping point for today, unless you have any questions, which I'm happy to answer.
Questions?
But as people studied these chiral waveguides, for example, on topological edge modes and photonic lattices and stuff like this?
I can't think of a concrete reference, but I would guess the answer is yes. Okay. Just for this, for the reason that, right, I mean, a minimal model has to have this type of structure, so even if I don't know the paper per se, I wouldn't be surprised if people have written it down somewhere.
Okay.
So it's more like 2 different questions. The first one is like, And what we can tell about the nearly resonant phase of the wave, for example, around that zero in the graph that you draw on the last board, what can we say about that regimen?
Oh, what, like the pi phase shifts?
Yes, yes.
Right. So we'll use it. We'll use a similar idea later when we construct a gate. So I can only offer kind of a hand-waving explanation now. But imagine I could kind of design a slightly fancier atomic system where essentially I shine in a first photon, and then, or I shine in a first pulse, which can either have 0 or 1 photon, and then depending on whether it has 0 or 1 photon, it either makes that atom kind of stay there or effectively disappear. So remember, if it has 1 photon, I could try to store it in the atom. Because the atom is a 2-level system, it then can't scatter another photon, so I can essentially make it disappear. And so now when I shine in a second photon, that second photon effectively sees either 0 or 1 atom. So then it'll transmit past that point, but it can either pick up a 0 phase shift, a trivial phase shift of 0, because there was no atom, or it can pick up a pi phase shift. And so now you can see that, or maybe appreciate that that could be a photon-photon phase gate. I'm not sure if that answers your question.
Yeah, actually answers both of them. Thank you.
More questions?
What? Maybe it's closer.
So what did we, because, okay, one parameter which I'm missing here is like kind of the energy scale between like the ground state and excited state, and like where did we hit it? Like, is it like in the Heisenberg picture, like hidden, or because like it seems that this difference is corresponding to like k equals 0 or something. So just don't explicitly see like where did we set it.
Yeah, sorry, maybe I should have explained that better. So the honest thing to do, so if you want to kind of connect to physics, the honest thing to do would have been to include, okay, the photon dispersion relation, but also to say that, okay, I can say my ground state would be 0 energy, and then this term here would give my excited state an energy of omega naught.
Mm-hmm.
So then if I did the same calculation, you would get exactly the same result here, except the k vector at which you pass through the resonance would be omega naught over c. Okay, and then the bandwidth at which you go from kind of resonant to non-resonant, that would be gamma 1d. Okay, so that's how the resonance frequency and gamma 1d are encoded in the problem. Maybe I can also give you a hint of what's to come. So if we talk about just real energies, so a typical atomic resonance frequency is in the visible. So omega naught would be hundreds of terahertz, whereas a realistic kind of emission rate is like a few megahertz. So the atom is actually a very high Q resonator, if you want. And the fact that it is a high Q resonator, that actually makes it easier to kind of integrate out the field. So the same as when you have a high Q resonance, when you shine light through such a system, you'll get a lot of dispersion and delay. Essentially, 99.99999% of that delay and dispersion will be coming from the atoms, and not the delay of free space, not because you propagate at a finite speed of light. And so the fact that the speed of light could be finite or infinite and you still get the same answer, that means that you might as well take the speed of light to infinity. Then you can exactly integrate out the fields, and then you'll get a much simpler description just in terms of the atom alone. So that's actually kind of one of the key ideas underlying the spin model.
My question concerns the chirality. Where is contained? Like, is in the phase that is always proportional to the path that has been done, that just to understand why it is from the Hamiltonian, where can I see that is directional?
Yeah, so it comes from the fact that there's only a single flavor of, well, I guess you could say it two ways. That okay, yeah, there's maybe two alternative ways you can think about it. I'll give one, and if you're not happy, I can present the other. So one way to think about it is that here I only have a single flavor of boson. So in particular, my dispersion relation, omega of k. So I have this mode here, which represents my A of k. So if I wanted a back propagating field, left propagating field, I should maybe label these AKs with an extra index right going. And then I should add in a separate set of photonic modes, which I'll call left going. And that would allow for propagation in both directions. So that's one way to understand how it's effectively chiral.
Okay, thank you.
Are there more questions? Okay.
If you want a more mathematical answer, like one nice thing about this model is we get a first order differential equation for the field. Of course, you know that if I look at even classical Maxwell's equations, the real wave equation is second order. And so one way to, which is fine, but it turns out that this kind of first order equation is easier to deal with or solve mathematically. So the way you get the first order is essentially to kind of extend the dispersion relation off to minus infinity. Another way to get both directions is to kind of close off these illegal modes and get a dispersion relation like that. Then you would still have one photon flavor, but then the price you pay is the second order differential equation instead of first.
So if we have a degeneracy in the system, your answer is it will work in the degeneracy case. If you in your system in the eigenstate, if you have a degeneracy in the system, the answer is it will work.
I'm not. When you say degeneracy, you mean like can I have two different eigenstates with the same EK?
Yes.
Not in the chiral waveguide. So so for the chiral waveguide, this label of k and the corresponding energy is really distinct. If you have bidirectional or even free space, then it's not true. So in free space, for example, the magnitude of k alone sets E of k, so I can have light pointing in any direction. And then I can have degeneracies. But for a chiral waveguide, I have a kind of one-to-one map. I'm not sure if that answers your question.
Yeah,
More questions? Okay, if we don't have more questions, so let's thank Darrick. I think he will continue tomorrow. We'll come back in half an hour then.